All right, hello everyone. Let's get started. So today I was thinking that I would mostly go over the project, and I would go over a little bit more about hash tables, probably. We basically covered everything about hash tables last time, so maybe I'll just do a little bit of a review before we get started, and then let's see. No, all of that is not what I want. I want the hash tables thing that I made. Oops. So, remember what a hash table is. Basically, a hash table is just a fancy array. Remember that basically the idea is that there's some hashing function that will take your key values and it will convert them into indices for the array, and then you modify the array size. So really, if it was just that, then that's all I would need to say, right? Because if that's all hash tables were, then it would basically be about 2 or 3 minute lecture. The only thing that really makes hash tables interesting is the fact that sometimes two things can hash to the same value. And so remember what they do if you do that. So either you can use a secondary data structure. For instance, here we're using a linked list to resolve hash collisions. So I think that our hashing function in this case was 3 times x plus 5, right? Mod whatever the table size was, so 1, 2, 3, 4, 5, 6, 7. So it was 3x plus 5 mod 7, and that was our hashing function, our total hashing function with the modulus thing. So you see here that, I guess, what, 3 times 3 plus 5 is 14, so that's 0. 17 times 3 plus 5 is 56. Divided by 7 is 8, so that's 0 mod that, and then 10 times 3 plus 5 is 35, which divided by 7 is 5. So basically all of these 3 keys map to the same value. And so that's why you have to use a secondary data structure to resolve hash collisions, at least for closed addressing. So closed addressing, all that means is that whenever you hash something, it only goes into the segment that is given by that hash key. So that's what closed addressing means, and that's how we distinguish it from open addressing. So none of this is relevant to your project, on the other hand, because you're going to be using open addressing for your project. Here's open addressing, right? Open addressing is if a particular slot is filled, you try a different slot, right? But how do you try a different slot, right? You need to know, there needs to be an algorithm that tells you which slot to try, because if you tried just some random place, then you wouldn't be able to search for it. So basically here, this is, remember what we're calling linear probing. Linear probing is where if you get, say, Julia, who has a hash key of 17, remember 17 times 3 is 51, plus 5 is 56, and that's divisible by 7. So since that's divisible by the table size, we know that that will hash to position 0, but 3 comma Eric is already in position 0. So what we have to do is we have to make sure that when we stick in 17 comma Julia, that we stick it in at a place where we can find it. And so if we're going to use linear probing, what we do is we just say, well, add 1. And this space was empty, so we stuck it in here. And then you do it again if you get, say, 10 comma Archie, right? 10 comma Archie also hashed to 0, and so you would say here, here, and then here. So, yep. So that's how linear probing works, basically, is that you just keep going until you and I guess the only other question is what happens if you try to linear probe and you found something with a different key value? The answer is actually that what you have to do is you just keep probing. So it's possible that you will have things that hash to 0 even past things that hash to other values. And it's a little bit dangerous because you have to make sure that everything shifts back properly. Otherwise you might end up with some problems. And I'll explain that in the context of the project as well. And so remember the difference between linear probing and quadratic probing. So linear probing just goes to the next spot. Quadratic probing will do something like this. So, basically I just cleared out a hash table. This is of size 10. And I'm inserting, say, 3 here, right? So 3 goes into the slot 0, 1, 2, 3. So this is the correct slot for something that hashes to 3. And remember, I'm just using the hash function hash of x is equal to x. You might think, well, that's a terrible hash function. And sure. Actually, in Python dictionaries, that's the hash function that they use for integers. They actually don't hash them, they just mod them by the table size. And then they assume that most users are going to give them relatively random inputs. And so you're not going to cause too many hash collisions. At least that's what I think I read when I was reading through the code, the C code that generates Python. So, okay, and then here, if you put in 33 will, this is just like linear probing, right? I even wrote it up here. Because you're going to stick 33 in the next slot. But the reason is because 1 squared is also equal to 1. So when you do 3 plus 1 squared, that's where you're going to go. And then 2 squared is 4, so that's where the next one's going to go. 3 squared is 9, so this is where the next one's going to go. These two aren't here yet, right? Because we haven't... 3 squared is 9, so the offset will be 9. And then the offset will be 4 squared, which is 16, so this is the next one. And then finally, the offset is 5 squared, which is 25. 25 mod 10 is 5, so the offset is just 5. And so this is where the last one goes. And then so 43, right? 43 is a problem because remember what's going to happen if we try 43. You'll say, okay, cool. I tried I tried 5. 5 squared is 25. 6 squared is 36. Well, I already have something that hashes to that same position. And so then I try 7. 7 squared is 49. I have something that hashes to the 9th offset. 8 squared is 81. I have something that hashes to the first offset. 100, well, that's 0. 121, 144, 169, etc. 196, right? So basically, the hash keys, so that's a good question. Why would you ever use quadratic probing? The reason why you might use quadratic probing is because you see that it kind of more evenly distributes your the values around in your hash table. And so that's kind of why you do it. You don't do it because, in fact, I haven't actually seen anyone use quadratic probing. It's just something that's taught in all the textbooks. It also creates, as I said last time, it creates a bunch of weird number theory problems because basically if you have a hash table and the hash table size is m, then the question is there a solution to the equation x squared mod equals that offset mod n? And so for some of them there are, but for instance here you see that there's no solution to x squared is equal to 2 mod n, or x squared is equal to 3 mod n, or 7 or 8. And so for every different table size, there's going to be residues, they're called quadratic residues, which are either true or false. And so some of them are quadratic residues, like 1, 4, 5, 6, 9, and there's some which aren't, like 2, 3, 7, and 8. And it's completely dependent on the table size. Let me do another example to show you that. Actually, I really just want to open the SVG of this, so let's see. Do I have it here? Yes, I do. Hang on. Let me see if I can open this. Open? Recent. Oh, wonderful. Hash tables. Let's see if this explodes. It does not. Okay. That is great. So I just want to review all this stuff, and then I'll get into the project description in a second. So here's basically, let's do another example where we say, yeah, let's take 7 things, and then let's see what happens, right? So let's say we insert something. Let's say we insert, let's decrease this font size. So let's say we insert the element 15, and remember we're going to use the h of x is equal to x, the identity hash function, and just mod it by 7. So 15 mod 7 is 1, right? Because 15 is equal to 14 plus 1. So that's where 15 is going to go. So I guess now we need a bunch of things that also mod to 1 mod 7. So what's another thing that mods to 1 mod 7? I guess 22, but that's boring. Let's make it 29. That's less boring, I guess. And so if we look at 29, right, and we use quadratic probing, what we're going to do is here we're going to do the offset of 1, right? So this is offset 1. And then what we're going to do is let's insert another one. So what's another one? So maybe 71 is also 1 mod 7. I don't know if that's interesting or boring, but whatever. So here, 71 is going to try to mod, it's going to mod by 7, and it's going to try to insert into here, and it can't. And so then what you do is you say, put it here, and then you say, okay, the offset is now 2, and I have to square it, so it's 1, 2, 3, 4, so 71 goes here. And so... And so then what do we do now? Let's pick another number. Let's say, 85, right? 85 is also, 85 is basically 15. So the offset now is 9. So 9 is bigger than 7, so actually this is an offset of 2, right? So what we actually do here, because we're modding, this will be an offset of 2. And then let's see, can we keep this going? How long does this keep going? And so the answer is, let's try another one. Let's try to insert, say, 50, right? 50 is, so 7 times 7 is 49. 50 is 1 plus that. So, okay, so we've done that. And so now the question is, what is the next offset? So we've done offset, really I should say, this is offset 9, right? Which is also equal to 2. And so in this case, what we're going to do, the offset needs to be 16. And so 16 mod 7, right? That's 2. So 16 mod 7 is equal to 2. So it's the same offset again. And so what we would try to do is we would try to insert 50 into here, and that wouldn't work. Well, first we need to try to insert 50 into here, then here, then here, then here, then here again, and that starts to indicate a bad sign. And then what you're going to do is you're going to say, okay, now I'm going to have to do 25. So 25 is 4 plus 21, so offset of 4. And so then 6, 36, 35, so the offset is 1, right? Because 36 is equal to 35 plus 1. And then 7 squared is 49. 49 mod 7 is 0. So then it tries to go back into here. So we see here that there are no solutions to, so if you have like x squared, actually maybe I'll just do it using, so if I just say there's no solutions of x squared is equivalent to, say, 3 mod 7, right? Come on, you know you want to do that. Almost. Okay, good. Let's see now, where did it stick it? So basically, this equation here has no solutions. And so if you're interested in all of this stuff, I would actually say that there's the theory of quadratic residues. And so there is a bunch of stuff in elementary number theory that tells you when these equations work and when they don't. So if that stuff is interesting to you, there is a direction to go there. But if you go back and think like, wait a second, aren't we just interested in arrays and hash tables? And isn't this like really complex? And doesn't this do kind of things that may or may not be good or bad, right? So 50 never gets inserted. Let me make 50 red. So 50 never gets inserted. And so it's hard to know what to do if you get a hash table like this. So there's a bunch of different solutions. Sometimes people, when the hash table fills up like this, what people do is you make the hash table bigger, right? Alternatively, you can throw an exception or something like that. So most hash table implementations, at least like the Java hash map, Python dictionaries, etc., their solution is always to make the hash table bigger. They never throw an exception. And the reason why they don't throw an exception is because they don't actually tell you the size of the hash table. They don't tell you how their hashing is working on the inside. They don't really tell you how, all the different stuff that they're doing. So the point is that they're just going to make the hash table bigger. But then the only problem with that is that when you change the hash table size, what were all of these positions dependent on? What was the last thing that we had to do? Right? We always were modding by 7 in the end. So the biggest problem with making the hash table bigger is basically that you have to reconstruct the entire hash table. Whoops. So as soon as you make the hash table bigger, you have to reconstruct the entire thing. So that's the biggest downside. So because all of the key, I really wish I would stop doing that. There. So basically what you have to do is you have to take everything out of the old hash table, you have to rehash it with the new table size, and then you have to reinsert it into a new hash table and then clear out the old one. And so that's a big, expensive operation. So basically when they say something like, oh yeah, like hash tables are O of 1 on average for insert and delete, that's true, mostly. The things that can really cause you to have issues is where if you have to reconstruct the entire hash table, the reconstruction operation is an O of n operation. But if we amortize, then we'll see on average the cost of operations is still O of 1. And let me explain to you why. Let's say we're using linear probing here. So what we know is that in order to have to reconstruct the hash table, how many insertion operations did we have to do? Right? So in order to reconstruct, we have to fill up a hash table. And so the number of operations needed before a reconstruction is triggered is approximately n. Right? Especially for linear probing, that's definitely true. For quadratic probing, you need to make some arguments. The arguments that you basically have to make is that the number of quadratic residues is approximately n divided by 2. And so even though it's n divided by 2 would trigger a reconstruct, it's approximately n in terms of big O, right? Because this constant will eventually get absorbed in the big O constant. So the point is that even though it's n versus n over 2, it doesn't really matter. It'll still run amortized with O of n operation, or O of 1 operations. And let me show you why. Because basically if you say, I'm going to do n times the number of inserts, which is going to be an O of 1 operation, right? Plus, after that, I have to do an O of n operation, right? So n times O of 1 operations, that is an O of n total operation. So this is O of n plus O of n, which is equal to O of n. But that's for n operations, right? Well, technically n plus 1 operations if you count the reconstruct. But I'm just going to count it as n total operations. So the point here is that given that we've done, it's an O of n thing, but there are n operations, that means that if we take O of n divided by n, this is back to O of 1 again. So that tells us that on average, and that's what amortization means, on average we expect there to be constant time for our... I mean, why would you resize when you can make it? So that's a good question too, when we expect a constant time for our operations. But the one thing I'll say before I answer that question is, but you can't expect each operation to be, oh, thanks. It'd be nice if I hit 100,000, right? But I'm only at 500 subscribers. I don't know. I'll have to think about it. Maybe I'll take some super chats. I'll read whatever you guys have to say. So, okay. But even when the amortization of the operation is O of 1, that doesn't mean that the total cost of any operation is O of 1, as you've just seen here, right? There's like a 1 over n probability that we're going to run an O of n operation. And that's a real problem, right? Because it's a real problem if your algorithm is, say, running online, like on the internet or something. You have to be careful that, because if each O of 1 operation, say, costs 5 milliseconds, that's about the amount of time that you would expect for, a server to respond. But if n is equal to 1 billion, and then it takes the server 2 hours to reconstruct the hash table, the user at the other end of the web browser is going to be thinking to themselves, what happened, right? So it's always possible, given a large enough n, that the O of n operation is going to cause issues. So in general, if you're doing something that needs to be fast, a lot of times what you can do is you would have like a separate process as the hash table reaches its load factor, the critical load factor. Remember what I told you about load factors. Load factor is often described as a lambda of a table, which is equal to the number of elements in the table divided by the size of the table, right? And so if you do this lambda load factor and it reaches a certain critical value, you can actually begin the reconstruction of the hash table in a separate thread, or maybe offline or something like that. And then when the next hash table is online, then you transition to that hash table or something like that. So you would have to think about a way to kind of have those things be done in parallel, and maybe every time the user inserted something, it would insert it into the old hash table and into the new hash table until, of course, both tables matched and you could delete the old one. And so your question is, why would you ever declare a small enough hash table that you would reach the why would you ever declare a small hash table? Why not just declare a large one, so large that it'll never reach that critical load factor? And the answer is mainly because, for instance, say in Python, right? You don't really think too hard about creating a dictionary. So remember, in Python, you can just be like, my dictionary is equal to a new dictionary, right? And then you can say other dictionary is equal to this, and you can say third one is equal to this. And this is going to go lickety-split, right? This is going to go real fast. Python is not going to spend time allocating 400 megabytes to each one of these, right? Because currently they have 0 elements in them. And so, for instance, here, if then you did like my dictionary.append, like, or not append, but if you did say like my dictionary of some string, right, is equal to some key times like 1,000,000 operations, then probably this hash table here was created with some default size. That size is not 1,000,000, right? And so once you insert the 1,000,000th element, it's probably going to increase its size a few times before it hits 1,000,000, right? Because like here, maybe you allocate a hash table of just size 10, right? Let's pretend that the hash table is of size 10 by default. I don't know why 10 is good or bad, but 10 is fine. But then once it gets up to, say, 5 elements in the hash table, let's say that once you get up to 5 elements, it says, oh, that's too much of a load factor. Let's increase it to size 20 or 100, right? And then once it starts getting up to size 100, you're like, ah, crap, like we have to increase the size again. And so it's just something that, the only reason why you don't declare it to have infinite memory is basically because just practical constraints, right? Computers don't have infinite RAM. That's the real issue. So if you have one large hash table, say you're going to have a hash table of all the people in the country or all the people in the world, right? That's a large hash table, and maybe you would create a hash table of size like 20 billion, I guess, just so that you could stick everybody in the hash table and avoid too many hash collisions. But then you see 20 billion is kind of large, right? So 20 billion is records is a large thing. You know, you need to calculate the total space is like 20 billion times size of record, and that'll give you total RAM space. So it's actually possible in a lot of cases that you will never even be able to load the entire hash table into memory if you're doing something this large. I'll say that 99.89% of hash tables are never that large, obviously, but like if you ever create something of that size, generally you'll need a hash table with some kind of like caching that goes to disk and then pulls from disk, etc., which increases the complexity of the implementation significantly. But it's really the only way, because you're not going to have enough RAM to store. If a record is anything more than a few kilobytes, you're not going to have the amount of RAM necessary to store something like this on any computer, really. Maybe on like the largest supercomputer stuff or whatever, but probably not. So that's the reason why we even have to talk about resizing, because when you resize, you basically reach a critical lambda value, and then it triggers a reconstruction of the table. And so remember that you want to keep lambda low. I would say that a good lambda is like, it's always good to have maybe 4 times the amount of space. Once you, like, this is a good lambda that avoids a lot of collisions. On the other hand, if you have a lambda value of, say, 0.5, you're going to see a lot of collisions. And just remember, it's mainly because the probability, every time you increase the lambda factor. The lambda factor is also equal to the probability of a collision, right? So you can think of the lambda factor as two things. It's the filledness of the table, but it's also the probability of a collision. And so if you want to reduce the probability of a collision, you have to make the table size larger. If you don't care as much about collisions, you can let lambda get larger, but then every time you get a collision, you're going to have to do some linear probing, quadratic probing, or using some separate hash function. One of the three canonical methods, or if you can come up with a new method of hash collision resolution. But those are generally the three that we talk about. We either talk about collision resolution, at least in open addressing, with linear, quadratic. You could technically do cubic probing. There's no rule against it. Quartic probing. Again, there's no rule against it. Some polynomial probing. No rule against that. There's all kinds of strange things you could invent. The only reason why you generally don't do complicated probing algorithms is because you want... So the rule in life for a hash table is the hash function should run very fast. And so now you're like, well, what does very fast mean? Very fast generally means O of 1, but a fast O of 1, right? So it should not depend on the table size, but it should also not really depend too much on the key. It should be able to run quickly based on any key that you insert. And that is something. Okay. So let's talk about the project a little bit. I think I've gone over everything about hashing again. Hopefully you vaguely understand what hashing is supposed to do, based on the previous lecture, really. So let's talk about the project. So, okay. What is the project? So in the style of 341 this semester, right? This is a 341 semester where basically all the projects are, well, not all, but essentially the projects are create an A of B's, where A is some kind of data structure and B is another kind of data structure. So you want to create a hash table of heaps, right? And so, all right. So implement a heap and a hash table. To implement using linear probing. Notice here they're giving us the easiest possible collision resolution method to handle hash collisions. And then to practice writing templated classes. So we'll talk a little bit about templated classes today, and we'll talk a little bit about other things. So, okay, let's look at the hash.h and heap.h. Why not? So here is the hash.h. Actually, maybe I'll just pull it up in CLion. Just have to make sure I don't. This is. This is not the right project. Let's see here. Okay. Cool. All right. Do I have any? I don't think I made any real changes to this part. Okay. So this part's safe to show. All right, so let's look at this thing. Let me increase the font size, I guess. Hold on. Okay. So basically, they declare this class for you. So we're going to use function pointers again. They're going to give you the hash function. So hash fn, right? This is a type def of an unsigned integer. And the reason why it's an unsigned integer is because you're going to mod it, and then it's a hash function pointer, and it's going to eat a string. So in this case, our key values are not going to be integers themselves, they're going to be strings. And so, yep. Did I actually write this? I guess maybe I didn't write this or something. Should return hash table. Maybe I didn't even write this. I implemented most of the project, but maybe I didn't implement certain parts. So it has a constructor, destructor, copy constructor, etc. Basically, the only thing here that you have is you have a hash function, you have the current number of things in the hash table, and you have the so you have the total size. So the good news for you is that the total size of the hash table never changes. So we're not actually, so you notice that here there's no resize method. You don't have to implement one. Once your hash table fills up, you're done. That's it. Okay. So, and then the last thing here is a heap pointer, right? This is going to be your array of heaps. I think I was able to implement this without any helper methods, but you're permitted to obviously make some helper methods as you want. So, yep. So this is the hash table class. So remember, we're going to be using linear probing. So what does linear probing do? It finds the location, and then if that location is filled, then it's going to keep probing until it finds a non-filled location, and then it's going to insert there. And when does it stop? It stops not when it reaches the end of the array, but when it loops back on itself all the way to the beginning. So generally, I just count from, say, 1 to the size of the thing and just do a for loop or a while loop or something like that. So this is actually the easier part of the project, I would say. One way to test this, if you want to test this, is you can always... Yeah, one good way to test this would actually be to copy and paste this class, and instead of having a heap here, you replace this data type with something else, and you can test it on that. Like just ints, right? Or strings or something. Okay, and so then, so that's a hash table. There's really not a lot there. All you have to do is do insert and get next. So get next retrieves and removes the highest priority order of the type indicated by key. So get next is actually not calling the, so it's calling the hash table. It's finding the element and it's finding the key in the hash table, but it's also deleting out of the heap, right? That's what the point of this function is. So this object is just inserting into the heap at, whatever the key is, and this is deleting. Oh yeah, and then the other thing to say is that objects need two things. So an object class has to have, for instance here, let's look at car.h. Car needs two things. Car needs key, and car needs priority. So those are the two things that you need. So key is used to get the key of the object for the hash table, and then priority is used for the heap. So this is basically an example of an object, right? So yes, so basically this is used for the heap, this is used for the hash table. So technically you are completely within your rights to write these two things almost completely separately, right? Like the hash table and the heap have almost nothing to do with each other. And let me scroll up really quickly. All right, so as you notice here, basically all this heap has is an insert, a read top, and a remove top, right? And it's also a template class. So maybe I'll talk about template classes in just a second. So this one is using the priorities, and you notice here that basically here they just have a vector. So you can't do a leftist heap. You can't do A skew heap, you can't do a binomial heap, even though I know everybody wants to do a binomial heap. You can't do it. Sorry. The only thing you're allowed to do is the vector heap. But as you probably know, the vector heap is kind of the easiest heap, right? I've implemented one in class before. Remember how you have to do it. So basically, in the vector-based heap, let's see here. No, that's not what I want. This is what I want. Yes. So for the vector-based heap, remember that if you have a vector, let's just do a vector. Yep. And then let's delete all of these values. If we insert something here and we say, so remember that the 0 value isn't used. I have a hint for you about the 0 value. So maybe you actually want to consider using the 0 value, even though the heap doesn't need it. My hint for you is that maybe you want to keep this value. So this is the index 0, and we're not going to use it, okay? Because if you notice here, I'm only showing one thing. Okay, so here's index 0. We're not going to use it. And the reason why we're not going to use it is then it makes the calculation much simpler. So remember that the two children of any parent, so if you have a node at position P, the two children, the left child is at position 2P, and the right child is at 2P plus 1. And so, for instance here, let's say that we insert something. Let's say we insert 71. And then let's say we insert 32, right? And so this is going to be a max heap. Is this thing a max heap or a min heap? Now I actually forget. Is it a max heap or a min heap? A max heap or a min heap? It's a max heap. So basically, if you insert this, you're going to stick it at the end of the array, which is technically here right now. And then you're going to check with the parent, right? So how do you check with the parent? So you always divide by 2. The index here is 2. So you check to see here if the position is, if the thing at position 1 is bigger, and it is, so you leave it. If it were 3271, then you would swap, right? So this is basically the data structure. This is the heap that you get to do all the swapping on. So here, if we insert 5, then basically the structure that we're making here is that 71 is the root, the right child is, or I should say the left child is 32, the right child is 5. Right, so that's the structure we've currently made. Now let's insert, say, 46. And let's insert that into this position. What is this position? This is 1, 2, 3, 4. So this is position 4. And so what happens when you insert something into index 4? You then have to check its parent, right? So you have to check the thing at index 2. So the thing at index 2 is actually less than it, so you have to swap them. So you have to swap them like this. And basically what that's doing is it's saying that we've inserted this node over here as the left child. And then remember that in order to make this a heap again, you have to swap like that. And so that's basically how you play this game. You'll write some kind of, you can either write a helper function. Basically, I tend to call it percolate up and percolate down. You can also just write it. I didn't actually even use a helper function. I just did it at the end of insert and delete. So remember how you have to delete something from a hash table, or from a heap. Right, so how do you delete something? Let's say that we have a few more elements in here. So let's make 25, and then I'll make this 3 so we don't have to swap. So this is actually a heap. So how do we delete an element from the heap? So you always look at element 0, you pull this element out, right? So this is the element we just deleted. And then what you generally do is you take the last element, you put it up in the root, and then what do you have to do? You have to compare it versus its left and its right children. So you say, am I bigger than 46? No. Am I bigger than 5? No. So who's the max, right? So that's how you delete. You take the last element, move it to the root, and then you delete downward by picking the max element and swapping on the way down. That's what I'm calling percolate down. So basically in this case, what you'll do is you'll say 46 is the maximum, so I will swap these two. And then the children of this one are these two, right? Because the children of this is, the children of 1 is 2 and 3. The children of 2 is 4 and 5. So now you have to pick the max of these two, so you'll say the max of these two is 32. So now I'm going to swap 32 with 3, and then that makes a new heap structure. And so remember that the heap structure isn't exactly sorted, but the reason why it's okay is because this parent has these two children. This node here, let's see, so this one has these two children, this one has these two children, and so if you put like a 16 in here, then the point is that 32 would have what? What are the children of 32? So this is index 2, this is the index 3, index 4, so these are the two children of 32. So this is a child of 5, right? Because here, this is index 3, and here this is index 6. And so in order to make that work, what you're going to have to do is you're going to have to swap that. And then, of course, if we had an index 7, these two would also be the children of index 3. So it's always just 2 times p and 2 times p plus 1. So these two are the children of 3. 4 would have children 7 and 8, or 8 and 9 out here, etc. So every node here has 2 children. The 2 children are, 2 times whatever plus 1. Okay, 2 times whatever and 2 times whatever plus 1. Okay, so this is basically exactly how you're going to do that part of the heap project, right? You're just going to implement an array-based heap. You should do that in the next few days, hopefully very soon. And you should test it independently, right? You don't need to implement anything about the heap to test your, or I'm sorry, you don't need to implement anything about the hash table to test your heap. So test your heap out before you even start on the hash table, okay? And so the reason why you want to do that is because if you have any bugs here, you want to find them first. And so generally it's pretty easy, but it's also very easy to make some simple mistakes with the indexing. It's easy to make some simple mistakes with the swapping. Basically, go down the list of all the simple mistakes you can make. You can make any one of those, and probably you'll make a few, because I generally make a few whenever I implement these arrays-based heap things. Even though it's such a simple structure, and I've done it like 10 times, I'll still screw up something simple. So, yeah, and so my hint is, here's my project hint. Because you need the key, right? So this has nothing to do with the heap itself, but it has something to do with the hash table. The hash table needs to know the key of the current heap that you're at, right? Because now, instead of just having a hash table of strings or a hash table of integers, you're actually having a hash table of heaps. And so look at where you can store a spare element, right? If there's nothing in position 0, or if position 0 is garbage, that's fine. But maybe, theoretically, just maybe, possibly, you could use position 0, not for the heap, but to copy an element that has the right key in it. So the first time you insert something into this heap, my hint to you is basically what you can do is just make a copy of that thing and just stick it into here as well. So if 46 is the first thing I stuck, well, actually technically 71 is the first thing I stuck in here. You could just stick a copy of this in. And then even though it doesn't have the same hash value, and even though, or the same heap value, and though technically all the things that you might say, like, oh, hey, it doesn't match, blah, 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 it's not in the heap anymore, the one thing you know is that the element that you insert first is going to determine what the key is. So 71.key is going to be the same thing as 46.key, the same thing as 32.key, the same thing as 16.key. So even if they have different heap values, right, even if they have different priorities, object.key will be the same for all objects in this heap. So that's the thing to understand, is that the key has to be the same. So you can use the index 0 to basically store a secret copy of the key. Now you're going to store an object, and even though that object may be removed from the heap eventually, you don't care, right? As long as the key value is maintained. So that's my hint for you here. It's probably a pretty good idea to do that, especially because what happens if this hash table, or if this heap becomes emptied out, and then the hash table tries to insert a new element with that key? The answer is, what if they try to insert, say, something with the same key, but it's not the same value, so say 84, then what you've done is you've secretly kept the key. So basically you know that the key is here, and then you can stick this object in here. And so that's basically the trick here, is that you should use this index 0 to remember the key value. All right, so that's something, I think. But at this point, I think basically there's nothing more to be said about the heap itself. So I think maybe I will talk instead about template classes. So template classes are weird. I don't know how well you remember them. So let's make a template class. What things are templated? And so here is my template example. And so let's make it a template class. The first thing I have to do, this is basically like getting rid of it out of the, I'm going to do this. So remember that all code for a template class, at least in terms of 341, has to go into your .h file. There are ways to make template code work with a .cpp, but they are complicated, and I tend to screw them up whenever I try to do it. So the safest way, and so remember when you're declaring a template, there's two ways to do it. You can either do it like this, where you have class T, where T is the object, or alternatively, there's like a more modern thing that they've added, type name T. So both of these are allowed to do it. Either way, that's generally that's how to declare it. And so let's make some functions. So let's say template example. Let's make a default constructor. What do we want this example to do? So this is a good question. What do we want this example to do? Maybe it can eat a T. And maybe it can spit out a T, right? So if you need a T to be a return type, so T is whatever the template is. So remember, basically, this can be set to integer, string, float, double, or it can be set to some kind of class object, right? So it can be a lot of different things. So let's put public here so that it works. And then I guess this is going to be a stack. Okay? The reason why it's going to be a stack is because I don't know. So maybe I need a linked list to do a stack, or Yeah, I guess I could use a linked list to do a stack, right? Nothing prevents me. So stack node. But this also needs to be templated, so template type name t, class stack node. Well, let's just make it a struct, I guess. So what's the difference between a class and a struct? Really nothing, except for the fact that by default, in a struct, everything is public, which is what I want. So let's make it stack, and then that. Okay. So basically here, we'll have what? And this is our first instance of declaring something that's a type. So whenever something is templated, it needs to have these 2 square brackets on it, and then you need to feed in the type that it is. So that's how you have to do it. You have to make sure that the type gets fed in these brackets. Technically, what you can also there are ways you can have 2 template parameters if you really wanted to. But in this case, we're just going to have 1 template parameter. Okay. So let's create this stack using maybe a linked list structure. And remember the way that I'm going to do it. So I'm actually... Oh, okay, that's... I'm always nervous when I get Discord messages, but that one is completely irrelevant. So let me show you how to declare these functions. So what you're going to have to do is, this is what I usually do, because I'm lazy. I copy, paste, like that. And then what I'm going to do is I need to do something like this. So it's going to be this t colon, like that. And so you notice the syntax here. It's going to be the class type, right? So the template example class. And you have to specify the template, not in the function name. The function name doesn't get the template. It's the class name that gets the template. And so that's how this works. And so now we can copy, paste, and copy, paste. And then here. All right. So what should we do here? I don't know. Good question. Let's set ptop equal to null pointer. Sounds safe, right? I prefer, I don't know why I prefer this. I think it's just more elegant. I like having an empty constructor. So how do we make a linked list out of a, or how do we make a stack out of a linked list? So I think the way that we generally do it is to remember basically this. Let me copy paste some of these. So basically the first thing in the stack is the thing, remember it's first in, or what should I say? It's not first in, first out. It's, what is it? Last in, first out. Let me try to evenly distribute these so that anyone who's a little bit OCD will be happy. So the way I'm going to do this is that this is going to be ptop, and hopefully this is going to be null pointer at the end here. So the point about this is that given that this one's going to be pointing to null, we'll know that once we get here, that's the end of the stack. Okay. And so when we push something onto the stack, what we'll do is we'll push something onto the front, right? We'll do this, and then we'll set ptop back 1, because the next objects are going to be arrowing this way. Let's see. There we go. And so, the next objects are going to be actually down the stack. So this is the bottom of the stack here, right? And that's why I'm calling this p top, because this is the top of the stack. And remember, whatever's at the top of the stack gets popped. So spit out is going to be the same thing as pop. Eat is going to be the same thing as push. So what we're going to do here is we're going to make a new, I guess here what we'll do is what? Stack node t pointer p new top equals stack node t that will eat a new t. Right, and so now you're thinking, wait a second, we need to fix the constructor. There we go. Looks fixed to me. What is it? Why does it hate this? Single argument constructors must be marked explicit to unemployed. Okay, I'll do it. Hey, if Clang wants me to do it, I'll do it. So, all right, and then here what we're going to do is we'll say p new top, p next is going to be equal to p top, which it's possible that it was a null pointer. And I think that's it, right? That's all we got to do here, right? Am I crazy? Oh, we should also have this constructor set the p next to null pointer. Otherwise, we will be in sad land. Okay, and then how do we pop? Right, so we say if p top, then what we do is we say p top is equal to p top p next. Right, so that could be null pointer. It's possible that it's null pointer. And so then what we'll do is we'll make a stack node t pointer old top equals p top, and then we will return. Oh, it's worse than that, right? And we have to make a t remember object equals old top object. And finally, what we get to do is we get to delete the old top, and then we get to return the remember object. And if we don't do that, then we should throw something, right? How did that work? How is this not giving me underlines and errors? I don't know. Maybe empty stack. So if you ever want to make yourself a new exception, I don't know if you've ever done this before, but one way to do it is just to do it this way. You can say class empty stack, and then just inherit a public exception, or I guess std exception. And you can always, you'll have to like include, I think maybe, what is it? And then really this is all you need to do. So this will make you a new exception, right? That you can throw. You technically don't need to inherit from this, but C++ likes it when you inherit from the std exception. At least Clang does. I think you can even put in an argument here, because it'll call the generic thing, you tried to pop an empty stack. You are bad. Right, so that's basically what you get to do here. So this is yep. So maybe I should do an assignment operator you want me to do an assignment operator? First things first, everyone's really quiet. Is this helping? Because I assume that you haven't seen... In fact, do you want me to upload this template example to the GitHub, maybe, so that you can review it, maybe, after class? Yeah, I think I'll do that. So, because here, it has basically everything you need for the templates for the project. So I think this is something that I actually screwed up when I was... when I was doing my thing. So I accidentally did something crazy here. But this is how you have to... So this is what the operator looks like. And so notice here, if you're going to return, right? If you're going to return, say, star this, what the heck is this, right? This is a template example T, right? So that's why you still need the template type name. But you're not just returning a template example, right? This is an error, right? You need to be returning a template example T. And here it's going to be template example T operator equals... Why does it not like this? Does not handle self-assignment properly. Shut up, who cares? What if I do this? Will this make you happy? Oh wait, but that's not RHS. Will that make you happy? I don't know. Okay, so sure. Okay, and so let's think about how to copy. So we need to basically have a clear. I'll make a clear method. Oh, I forgot, we should have a destructor, right? And we'll have a clear method. And so, okay. So how do we delete a linked list? Remember how to delete a linked list? Let's see if I remember how to delete a linked list without creating a, segfault. So here we're just going to call clear, and then we're going to set ptop equals null pointer. And so here what we're going to do is we're going to say while ptop, right? Yeah, we can just basically set old top equal to ptop, delete ptop equals ptop, p next, delete old top. There. And then of course you're like, but what the heck is old top? You can't just do that. That's not right. Stack node t pointer old top equals ptop. Now are you more happy? See what I do to make you happy? I do all kinds of things. So yeah, I think that works, right? Am I crazy? Why does it not like this? This value is never used. I guess who cares, right? Okay. So that should do it. And then at the end, let's just put the ptop equals null pointer in here. That way we can just call clear. Okay. And so now what was I going to do? Why did I do all this stuff? I did this stuff because I wanted to do the assignment operator. So while current, of course you've got to scream like, hey, what's current? So my current and then other current, right? And I'll make this equal to p-top. So what we got to do is we got to say if let's just do if other thingy dot p-top, then we have to create p-top is equal to new stack node t with the element is other te dot object, no, dot p-top object. There we go. Okay. And so let us define stack node t pointer current equals p-top. And now it's not null. And let's define other current as other te dot p-top. There we go. And so while the other current maybe this. What do you think? You think that's good? So if there's a next, then we'll copy the next and advance, right? Copy the next, advance. So let's do that. What am I doing? There we go, and then we advance. So we say current equals current p next. And we say other current equals other current dot p next. I think this should work, right? The whole point of this is that all of this garbage is just some example code that'll show you how to basically manage all the template stuff. I think this should actually compile. So let us make a template example. And now let us make a template example of ints. So template example, maybe of ints. My int example. And then let's make a template example of maybe string. Right, so let's include okay. Oh, I think we have to using namespace. And then, okay, so I'm not going to actually run any tests on it yet. Let's just see if this thing actually compiles. Oh, and so here, what you should actually do is just delete this file. No CPP file, just H. Right? Everything goes in the .h file. The reason is because if you put things in the .cpp file, I promise you that you will have linker errors. There will be non-stop linker errors. You will not be able to really get away from them. There are some secret ways. There are some secret ways that you can do it, but it is not pleasant, okay? So, like, it involves some real crazy linker tricks. But in general, you got to put all your template code in the same file. So you notice here that here's my class definitions, and then here's my code for those classes. So they have a comment in the code file, which is basically like implementation of template methods here. And so what they mean by that is you literally just right after this comment, you just implement your template methods, right? And that's all. That's what you do. So okay. It still doesn't think I handle self-assignment properly. I wonder what the Clang way is, the Clang tidy way to do it, because this would check for self-assignment, right? Okay, so let's compile this thing and see what happens. Let's see out something. We did not explode. So if this might be the first time that I would ever have made something like this that didn't explode the first time with templates. Yep. So basically here, like if we say my int example dot say eat 5, and so remember this is a stack, right? So we're eating 7, we're gonna eat 12, and then let's see out my int example dot spit out, and then let's even try the other one. I'm feeling and then let's see what comes out when we do this. Errors. Wonderful. Excellent. This is what I expect with templates. Cannot convert constant character 48 to empty stack. Huh. Cannot convert constant character 48 to empty stack. No constructor could take the source type. Maybe it doesn't like the string I put in there. Ooh, more errors. Did I even declare this? I didn't declare. Okay. Segfault. Let's see if it segfaults until it does the copy constructor. So I think maybe the assignment operator is causing that. Nope. Huh. Oh, I think it's segfaulting here. That's weird. Right, so let's say cout about to seg. Okay, let's see what happens here. And I actually don't think it's segfaulting. Let's see if it's actually throwing the exception. Catch stack empty stack es cout third stack exception. And if this happens, then I basically know what to do. Ah, see, that's a lie. It's not segfaulting. I bet that I need to make a not. Huh. But it should have some things in it, right? Because eat. Am I doing something stupid? Oh my god, I am doing something really stupid. ptop is equal to... I'm not done here. I'm not done here. Okay. There we go. There we go. I wasn't actually moving the ptop back. I was just not doing that. Okay, cool. So now let's try the other thing, because it'd be nice to give you working code. Hopefully this will spit out 7, right? Because this was spit out before we copied it. So let's see what happens. Wow. Okay, perfect. Perfect. All right, so I'm going to upload this code. You can play around with it. Get a good feeling on template classes. I think it's a good example because it's something it's not as long as the project, but everything that you need for the project is in here at some point, right? Throwing exceptions, making template classes, declaring variables that have template types, declaring new things with template types, right? So the syntax for the assignment operator, all that stuff, it's all in here, right? So that's what I'm kind of looking for. So it's not the project exactly, so I'm not giving you all the answers, but it is everything that you'll need for the project because it's all the template stuff that you're going to need. I think. If there's anything that we don't have, we can always add it later, right? Because there's no reason not to. Okay, so let me upload this right now, and I guess the lecture is currently done. Thanks, everyone, for showing up. I think maybe talking about templates was probably more useful, right, than doing more reviews about array-based heaps, because that's, I think you guys sort of understand array-based heaps. I'm hoping. I'm thinking. All right. So, okay. Go forth and conquer. Right? Get this done. All right?